Okay, let me continue with the last lecture about finding the roots of the nonlinear equations. The last lecture about the finding zeros of a polynomial. You know that a polynomial of degree n has the form p of x equal to an x to power of n plus an minus 1 x to power of n minus 1, and we continue in this shape until we arrive to a1x plus a0, and we have to suppose that an is not equal to 0. This is a polynomial of degree n. All of these an called coefficients of p. What's the problem now? The problem is that we are looking for the zeros of the polynomial. In fact, if you consider, for example, x squared minus 2 plus 2 x minus 3 equal to 0, we know that if we put x equal to 1 and x equal to minus 3, then if we call this polynomial p of x, then p of 1 and p of minus 3 is equal to 0. X equal to 1 and x equal to minus 3 called the roots of this polynomial. But we know that if the degree of a polynomial is more than 2, for example, n equal to 5, or for example, n equal to 7, then we cannot find the roots of the polynomial directly. So we have to use an iterative method, for example, Newton method. But there is a drawback here. What's the drawback? The drawback is that for using the Newton method, we have to compute p of x and p prime of x. And both of p of x and p prime of x needs lots of computation. For example, here, if you consider this one, and if you want to compute, for example, p at 2, we have to do one multiplication here, one multiplication here, and 2, in fact, add and subtract here. And if the degree of the polynomial increase, for example, consider n equal to 17, okay, then we have a lots of computation. I mean the multiplication and sum and subtraction, okay, for computing p of x and also p prime of x. And this is not easy, and it needs lots of costs. So we are looking for a new method, new technique to compute this, in fact, p of x and p prime of x with less computations, okay? But before that, we know that if p of x is a polynomial of degree n greater or equal than 1, then it has at least one root. It's maybe real root or complex roots. And in the general form, we know that a polynomial of degree n has exactly n real or complex roots. What do we want here? We want to find the real root of a polynomial. Okay? Now, and also we have some concepts about the, in fact, roots of the multiplicity more than one. for example, here if p of x is be equal to anx minus x1 to power of m1 x minus x2 to power of m2 until x minus xk to power of mk. Here, for example, we can say that x equal to x1 is a multiple root with the multiplicity m1. X equal to x2 is another root with the multiplicity m2, and so on. But now we want to find the roots of the polynomial with Newton method, so we need to have a new technique to compute p of x and q of x. Okay, let me show you something. This is a very simple corollary from the previous theorem. It says that if p of x and q of x be two polynomials of degree at most n. So if x1 and x2 until xk with k greater than 0 are distinct number such that p of xi equal to q of xi for I equal to 1 to k, then p of x are everywhere equal. But let me start, in fact, my main problem today. There is a technique called Horner's method. Horner was a mathematician that invented this technique. The Horner technique is a very simple and fast method for computing p of x and p prime of x at every point, for example, x0. Let me try to explain the technique, and then I give you some example and I teach you how can you use the Horner method for finding p of x0 and p prime of x0 for using the Newton method. Okay, let me start with p of x as a polynomial of degree at most n. Okay, we want to compute p of x0. Okay, so in fact we want to use an iterative method to finding p of x equal to 0. To this end, we need p of x0 and p prime of x0. William Horner developed an efficient algorithm with n multiplication and n additions to evaluate p of x0. What's the Horner method? This is the details of Horner methods. Let p of x be a polynomial of degree at most n. Okay? Now, if we want to find p of x0 for any x0, we let bn equal to an. And we construct a sequence like bk to form ak plus bk plus 1 times x0 for k equal to n minus 1, n minus 2, n minus 3, and 1 and 0. Okay? So, if we construct this equation, then b0 will be p of x0. In fact, this is a theorem that you can find the proof of this theorem in every numerical analysis book. So, in this technique, we only use n multiplication and n additions. Let me show you an example. For example, if you consider p of x equal to x5 plus 3x4 minus 3x3 plus x2 plus x minus 1. And you want to compute, for example, p of 2. Here, if you want to put 2 in the polynomial, you will have 5 multiplication here, 5 here, 10, 4 here, 14, 2 here, 16, 16. Multiplication, and 1, 2, 3, 4, 5 addition. Okay, but if you use Horner method, you need just n multiplication, I mean 5 multiplication and 5 additions, and it's very, very simpler than the usual method to finding p of x0. Okay, if you do something like this, then at the same time we compute the decomposition like this: p of x equal to x minus x0 times q of x plus b0, where q of x is exactly a new polynomial that the coefficient of the polynomial have been constructed by these in fact coefficients. Okay, now we know that in this decomposition, if b0 b equal to 0, then x0 is a root of the p of x. Okay, this is the Horner technique. But maybe something strange happened here. If you consider p of x as a polynomial of degree n, you keep a0 out and factor x from the first n minus 1 terms. So you will get an xn minus 1 plus an minus 1 x n minus 2 until a1 times x. Then inside this parenthesis you keep a1 out and factor from x and so on. Okay, the Horner method simply is simply the computation of these parenthesized expression from inside out. In fact, first it computes this one, and then the other one, and so on. But let me forget about the theory of the Horner method, and let me show you a relation between p prime of x0 and the Horner method. Now, we know that if we want to use a Newton method, we will have xn plus 1 equal to xn minus p of xn over p prime of xn. Okay, so we need p of xn and p prime of xn. We could compute p of xn by Horner's method. It remains to compute p prime of xn. The Horner method has a very simple solution to finding p prime of xn. Now, if we want to compute p prime of x0, you consider p prime of x at x equal to x0. But we had p of x equal to x minus x0 times q of x plus b0. Right? Now, if you compute p prime of x, it will be the first derivative 1 times the second one, q of x, okay, plus the second derivative times the first one. It means x minus x0 times q prime of x. Now, if you put instead of x, x0, this term vanishes, and here just remain q of x0. So if you want to compute p prime of x0, you can compute q of x0. What's q of x0? We showed you here. This is the q of x. Okay, but all of these terms that I mentioned in the last slides maybe seems very complicated for implementation, okay, but it's not. It's very, very easy, and you can implement easily the Horner methods. Let me show you the implementation of Horner's method by an example. Suppose that we want to compute p at 5 for the polynomial px equal to x4 minus x3 plus x squared plus x minus 1. Easily, you can draw a table. In the table, you put x0 in this place, x0 equal to 5, and you have to put the coefficients of the polynomial from the coefficient of the greatest, degree to the smallest degree. So you have to put a4 equal to 1. The coefficient of x3 is minus 1. The coefficient of x2 is 1. The coefficient of x is 1. The coefficient of x 0 is minus 1. Now, by the algorithm of the Horner method, you have to put b4 equal to a4. Please remember, bn equal to an. Okay, so b4 equal to a4 and it will be 1. And for the other coefficients, bk is ak plus bk plus 1 times a0. Let me write it here. bk equal to ak plus bk plus 1 x0, and let me transfer it here. bk equal to ak plus bk plus 1 times x0. Now, consider here, you have to, for example, for b3, you have to compute a3 plus b4 x0. Okay, b4 x0. So you have to compute b4 x0. b4, you multiply b4 times x0 and put it here and add a3 to b4 x0 to get b3. And in the same way, you have to multiply b3 times x0 and put it here. Look, b3 x0, put it here. 4 times 5 is 20, plus a2 is 21. For the other one, 21 times 5, we will put it here instead of b2x0. Is 105 plus 1 is 106. Remains b0. You have to multiply b1 times 5 is 530. And put it here, plus minus 1 is 529. Okay? And this one is p of 5. And we are done. You can see that we just one multiplication here, one multiplication here, one here, and one here. Just 1, 2, 3, 4 multiplication and 1, 2, 3, 4 addition. And it's all done. Now, when you find b0, you can decompose p of x as x minus 5 times x3 b4 x3 4 x2 21 x plus 106 plus 525. Now, if you want to find p prime of x, you have to construct a similar table and compute q of 5. Okay, so you have to draw another table and put x0 equal to 5 here, and you have to put the coefficients of q of x. This is q of x. Okay, you have to put the coefficients of q of x here. So the coefficient of x3 is 1, a3. Coefficient of x2 is 4, 21, and 106. And easily you have to put the new b3 equal to 1. 1 times 5 equal to 5 plus 4, it's 9. 9 times 5, 25, plus 21 is 66, times 5 is 330, plus 106 is 436. This is p prime of 5, and it's over. Now you have p of 5 and p prime of 5. So if you want to implement the iterative method, like for example Newton, you have p of x0 and p prime of x0. So you can find x1 by this equation. x0 minus p of x0 over p prime of x0, and then you will need p of x1 and p prime of x1 for the next iteration. So you can repeat these two tables to find p of x1 and p prime of x1, and you can continue to find x2 by Newton method, and so on. So here you can find the root of the polynomial easily without any problem. So if you want to consider the algorithm for Horner method, in fact we will have the degree of n and the coefficient a0 to an. What do we want? We want p of x0 and p prime of x0. In 4 steps like this, you can find both p of x0 and p prime of x0. It's very easy. You can implement it easily in MATLAB or Python code, and you can get the favorite result. This is all about the Horner method. I don't give you any other example. If you want, you can search in the internet and you find lots of examples, and also there are a lot of code in MATLAB, Python, and any other languages. So here I stop talking about finding the roots of nonlinear equation, and from the next lecture I will start about the interpolation, and there are a lot of very, very interesting concepts about interpolation in the next lecture. Please subscribe my channel and introduce my channel to your friends. Thank you.